Welcome to Mysteries of Earth. For as long as we've studied the cosmos, we've assumed that our destiny is bound within the sun's embrace. But what if that boundary is not permanent? What if one day humanity could step beyond it? At the farthest reaches of our solar system, subtle clues whisper of this possibility. Spacecraft drifting into interstellar space, theories of propulsion that challenge the limits of physics, and visions of journeys measured not in years but in centuries. Each discovery invites us to reconsider what it truly means to explore. In this documentary, we follow humanity's quest to leave the solar system. From the Voyager probes, our first ambassadors to the stars, to the bold ideas that could, one day, carry us farther than ever before. What challenges stand in our way? And if we do succeed, what will we find waiting in the endless dark? Join us as we journey to the very edge of the known. And if this story inspires you, don't forget to subscribe, share, and continue exploring with us here on Mysteries of Earth. At the farthest edge of our solar system, there drifts a faint signal, a whisper in the cosmic dark. It is not the voice of a star or the hum of distant galaxies. It is something far more improbable. The call of a machine built by human hands, carrying our story across the void. That machine is Voyager, or rather, two of them, twin spacecraft launched in 1977 on a mission that was never meant to last this long. They were designed for a grand tour of the outer planets, but today, decades later, they have become something greater. They are the first emissaries of humanity to touch the space between stars. The Voyager probes are, in many ways, our first steps beyond the solar system. Not steps of flesh and bone, but of circuitry and metal, steps made not by astronauts but by fragile messengers pushed outward on a journey with no return. Voyager 1 is now the most distant object humanity has ever created, more than 14 billion miles from Earth. Its twin Voyager 2 follows close behind, cutting a different path into the darkness. Together they drift beyond the sun's protective bubble, the heliosphere, into the vast and hostile medium of interstellar space. Yet, even as they sail into the unknown, they are still teaching us. When they launched, the planets beyond Mars were little more than distant specks. Telescopes revealed their outlines, their colors, their faint weather systems, but the details, the storms, the moons, the hidden oceans, were mysteries. Voyager changed that forever. As Voyager 1 approached Jupiter, it revealed a world alive with violence, colossal storms swirling for centuries, lightning that dwarfs anything on Earth, and a magnetic field so vast it could fit dozens of planets within it. But perhaps most surprising was one of its moons, Io, a volcanic world erupting with fountains of sulfur that reached hundreds of miles high. Until that moment, no one imagined another body in the solar system could still be volcanically alive. Saturn, too, was transformed from a ringed jewel glimpsed through telescopes into a dynamic system. Voyager showed us the intricacy of its rings, not solid bands, but billions of icy fragments, each orbiting in its own delicate dance. It revealed Titan's thick atmosphere, shrouded in golden haze, a world with chemistry that hinted at the possibilities of life's building blocks. Voyager 2 carried this exploration even further. It remains the only spacecraft to have ever visited Uranus and Neptune. At Uranus, it unveiled a planet tilted so dramatically that its seasons last for decades, and moons with fractured, frozen surfaces. At Neptune, it discovered supersonic winds and a moon, Triton, that spouts geysers of nitrogen into space. Another world far more active than we dared to believe. These discoveries were not mere curiosities. They reshaped our understanding of planetary science. They showed us that the outer solar system is not barren, but alive with activity, and that worlds we once thought frozen or dead may hold secrets still waiting to be uncovered. But the Voyager's greatest legacy is not only in what they discovered, but in where they are going. Beyond their scientific instruments, each spacecraft carries a message. Affixed to their sides is a golden record, a time capsule for the cosmos, engraved with music, sounds, images, and greetings from Earth in dozens of languages. It is humanity's first attempt to speak to the stars. It is unlikely anyone will ever find it. Space is vast, and the Voyagers are tiny. But still, the record exists. It drifts outward like a bottle in an endless sea, a declaration that we were here, that we looked outward, that we dreamed of connection. And in that way, the Voyagers are not just spacecraft. They are ambassadors. They are symbols of our curiosity, our restlessness, and our desire to know what lies beyond, long afar. Earth has changed. Long after our cities have crumbled, the Voyagers will still be moving through the galaxy. In 1 billion years, when mountains have risen and worn away, when continents have shifted beyond recognition, they will still be sailing through interstellar night. There is something humbling in that thought. 2 small machines built by people who could never follow them, carrying traces of a civilization still young in the cosmic scale. We do not yet know how, or if, we will ever leave the solar system ourselves. But the Voyagers show us that our reach has already extended beyond it. They remind us that exploration does not always begin with certainty. Sometimes it begins with a question, a risk, a simple act of sending something into the dark and listening for what comes back. Today, as we receive their faint signals, each photon of radio light crossing billions of miles, we are reminded that the universe is not just out there. It is something we are already touching, however lightly, however briefly. The edge of our reach is not a wall, it is a horizon. And with each step, each probe, each dream, each idea, that horizon shifts, pulling us onward. The Voyagers continue their journey into the unknown, but their story is only the beginning. For the question remains, if machines can leave the solar system, can we? And so, as we look to the future, we must ask ourselves what paths might carry us farther still into the true ocean of stars. In the night sky, the stars look so close. They twinkle like neighbors just across a quiet street. But distance in space is deceptive, for the truth is far stranger and far more humbling. The stars are unimaginably far away. The nearest star beyond our sun is Proxima Centauri. To the eye, it's just one faint speck among billions, barely noticeable in the southern sky. But in reality, it lies more than 4 light-years away, 4 years for light. The fastest thing in the universe to make the journey. Light itself, which can circle the Earth 7 times in a single second, takes over 25 trillion miles to cross the gap. How far is that really? Numbers like trillions are easy to say, but hard to grasp. So let's shrink the cosmos into scales we understand. If Earth were the size of a marble sitting in the palm of your hand, the Sun would be about the size of a beach ball 25 meters away. On that scale, the nearest star would not be in the same room or even the same city. It would be another beach ball more than 6,000 kilometers away. The distance from New York to London and back again. That is the immensity of interstellar space. If we set out for Proxima Centauri today, how long would it take? Suppose we traveled by car, speeding at highway pace, 60 miles per hour, day and night, without ever stopping. At that speed, the trip would last over 50 million years. Even a jetliner racing at 600 miles per hour would need more than 5 million years to arrive. What if we used rockets? The fastest spacecraft humans have ever built is the Parker Solar Probe, launched in 2018. At its peak, it will reach 430,000 miles per hour, fast enough to fly from New York to Tokyo in less than a minute. Yet even at that incredible speed, the journey to the nearest star would last nearly 7,000 years. In other words, every technology we possess today is hopelessly slow. On human timescales, the stars may as well be infinite. This is why interstellar travel is so daunting. The barrier is not a lack of will or even imagination. It is physics itself. Distance stretches so vast that even the mightiest rockets we can build barely scratch its surface. To cross the void, we would need to go faster. Much faster. Near the speed of light itself. At those velocities, Proxima Centauri becomes attainable within a human lifetime, 4 years at the very fastest, decades if we fall short. But approaching such speeds requires energy on a scale that borders on the impossible. Accelerating even a small spacecraft to a fraction of light speed would demand fuel greater than anything humanity has ever produced. And then there are the dangers. At relativistic speeds, even a grain of dust becomes a lethal projectile. The thin plasma of interstellar space, almost empty yet filled with particles, would batter a ship traveling near light speed as if it were flying into a storm of bullets. Engineering a craft to withstand that punishment may prove as difficult as reaching those speeds in the first place. The immensity of distance also carries a psychological weight. Human history is measured in centuries, our lives in decades. But interstellar journeys may stretch far longer. Even if we find ways to travel faster, the trips could still outlast civilizations, nations, even species themselves. Would we have the patience to embark on voyages whose destinations might not be reached for hundreds of years? Yet the very scale of the challenge reveals something profound. Distance is not just an obstacle, it is a teacher. It forces us to confront our limitations, to recognize the smallness of our reach compared to the vastness of the cosmos. And it reminds us that if the stars are ever to be ours, we must think in ways that go beyond rockets and fuel tanks. We must imagine new physics, new forms of propulsion, and perhaps even new definitions of what it means to travel at all. The void between stars is not empty. It is full of questions about time, endurance, and possibility. Can we find a way to bridge the gulf, or will the distances remain eternal, keeping us forever bound to our local star? For now, the immensity of distance stands as the greatest barrier to interstellar travel. But history tells us that barriers can inspire breakthroughs. The oceans once seemed impassable, until sails and compasses turned them into pathways. The air once seemed forbidden, until wings carried us into the sky. The stars, distant as they are, may one day reveal their own routes, if we dare to look for them. The Voyagers showed us we could touch interstellar space with machines. The question before us now is whether we can do it ourselves. And to answer that, we must ask, what engines could possibly carry us into the beyond? Everywhere we look in the universe, light is already there, waiting for us. It streams from stars, from galaxies, from the faint afterglow of the Big Bang itself. Light is the messenger of the cosmos, and it is also our jailer. For physics has placed a speed limit on reality itself, and that limit is the speed of light. No matter how hard we push, no matter how much energy we pour into rockets, engines, or dreams, nothing with mass can move faster. Einstein showed us this a century ago. As an object accelerates, its energy of motion, its kinetic energy, grows not smoothly but steeply rising toward infinity as it approaches light speed. Each increment of acceleration demands more fuel than the last until the required energy becomes infinite, and infinity is not something we can build. It is a simple, brutal truth. The closer we come to light speed, the harder the universe pushes back. But what does that actually mean? Imagine you are aboard a spacecraft racing faster and faster, approaching the Great Barrier. From your perspective inside, time begins to slow compared to the outside universe. A second aboard your ship might equal minutes, hours, even years for those left behind on Earth. This is not science fiction, but relativity, a law of nature written into the geometry of space and time. The faster you go, the more the universe itself reshapes around you. Push this idea further, and a paradox appears. At the exact speed of light, time itself would freeze. To a photon, if such a perspective could exist, there is no before and after. The entire journey from emission in a distant galaxy to absorption in your eye would happen all at once. This is why light can move at that ultimate velocity. It has no mass, no clock to tick. But for anything made of matter, for you, me, or a starship, that boundary is absolute. The light speed limit reshapes every atom of the stars. Consider Proxima Centauri again, just 4 light years away. At the ultimate velocity, light itself makes the trip in 4 years. A spacecraft could never do better. If humanity could somehow build an engine powerful enough to carry us near that speed, we would indeed arrive, but never faster than light itself. The universe is not negotiable. Even more daunting is what this means for greater distances, 10 light-years, 100, 1,000. Our galaxy stretches 100,000 light-years across. Beyond that, other galaxies float millions of light-years away. At those scales, even light becomes slow. The messages we receive from distant galaxies are postcards sent long before humans ever walked the Earth. And so when we talk about interstellar travel, Einstein's limit is more than a scientific detail. It is the defining wall of our imagination. It means that visiting another star, even the nearest one, is not simply a question of technology or will. It is a confrontation with the very structure of reality. Still, limits are not always prisons. Sometimes they are guideposts. Knowing that light speed is unreachable forces us to rethink what travel might mean. Perhaps the answer is not brute force, but subtlety. Perhaps instead of trying to break the cosmic limit, we must learn to bend space itself, to warp it, fold it, or tunnel through it. Wormholes, warp drives, and exotic physics all spring from this realization. If we cannot outrun light, maybe we can find ways around it. But these remain only whispers of theory. As far as experiments and engineering can reach, the speed of light stands firm. The Voyager probes, now drifting in interstellar space, move at a crawl compared to that ultimate velocity. Our fastest engines fall short by factors of thousands, even millions. And so the stars remain far, their light shining down as a reminder of how small our reach still is. Yet there is also hope in this limitation. Relativity does not make interstellar travel impossible. It only makes it hard, very hard. Journeys of decades, centuries, or millennia may lie ahead of us, long, slow voyages where patience matters as much as propulsion. We may never leap across the galaxy in a single bound, but step by step, system by system, the universe could still unfold before us. The speed of light is a barrier, yes, but it is also a challenge, a reminder that if we are to leave the cradle of the solar system, we must do so with imagination equal to the vastness of the task. For now, we remain bound by Einstein's law, as travelers walking along the shore of an ocean too wide to cross. But even here, at the edge of physics, new questions arise. If light speed is a wall, could there be hidden doors within it? Could advanced civilizations somewhere out there already know the paths that we have only begun to dream about? And so from the limits of physics, we turn to the possibilities that lie just beyond. Strange engines, exotic matter, and the daring hope that perhaps the universe has left us loopholes. If the universe has placed a speed limit on us, then perhaps the challenge is not to break it, but to get as close as we can, to chase the horizon with engines powerful enough to carry us across the dark, even if it takes decades, centuries, or longer. And so the great question becomes, what engines could carry us to the stars? The simplest rockets we use today are chemical, burning fuel to push hot gases out the back, inching us free of Earth's gravity. They are enough for the Moon, for Mars, for the solar system, but for the stars they are hopelessly weak. At their very best, they would take tens of thousands of years to reach even the nearest one. To go further, we need something far more daring. One of the boldest ideas was conceived in the shadows of the Cold War. It was called Project Orion. The concept was both audacious and terrifying: to build a starship that rode a series of controlled nuclear explosions. A vast metal plate at the ship's rear would absorb the shock of each detonation, transferring the energy forward. Imagine a vessel hurling itself across the void by setting off atomic bombs behind it. A thunderous leap, one blast at a time. The physics was sound. A ship powered this way could, in theory, reach a fraction of light speed. But the politics, the dangers, and the sheer spectacle of launching such a machine doomed Orion to remain a dream. Still, the idea lingers, a reminder that even our most destructive technologies might one day become engines of exploration. If not nuclear bombs, then perhaps nuclear fusion, the very process that powers the stars themselves. Fusion propulsion has long captured the imagination of physicists. By fusing light elements like hydrogen into helium, it releases energy millions of times more efficient than chemical reactions. A spacecraft driven by fusion could, in principle, run continuously, accelerating gently but relentlessly until it reached astonishing speeds. Projects like the Daedalus design of the 1970s explored this possibility: a massive two-stage fusion engine that could propel a probe to another star within a human lifetime. The engineering hurdles are immense. Containing and controlling fusion reactions in space remains far beyond our grasp, but every step toward fusion energy on Earth brings us closer to unlocking its promise among the stars. And then there is the most exotic of fuels, antimatter, matter's mirror twin. When a particle of antimatter meets its counterpart, they annihilate in a flash of pure energy. No reaction is more efficient. A single gram of antimatter, unleashed, could produce as much energy as a nuclear bomb. A rocket powered by this fuel could accelerate with breathtaking speed, potentially reaching close to light itself. The catch is cruel. Antimatter is vanishingly rare. We can make it only in tiny amounts at enormous cost inside particle accelerators. To build an antimatter rocket, we would need to manufacture and store it by the ton. For now, it remains more dream than plan, a distant glimmer of possibility. But not all starships must be massive engines of fire. Some could sail. Picture a spacecraft the size of a kite, its sails stretched thin and vast. Instead of wind, it catches light. Each photon carries momentum, and over time, the steady pressure of starlight can push a craft outward, faster and faster, with no fuel at all. A solar sail could drift on forever, gaining speed with each passing year. The Japanese spacecraft Icaros has already demonstrated this idea within our solar system. and others have dreamed of amplifying it further, not with sunlight, but with lasers. From Earth or from orbit, immense beams of energy could be focused onto a sail, driving it outward at tremendous velocity. This is the vision behind Breakthrough Starshot, one of the boldest projects of our time. Instead of building giant starships, the plan is to build ships no larger than a chip, wafer-thin probes attached to sails a few meters wide. By blasting them with powerful ground-based lasers, these tiny craft could be accelerated to a fifth the speed of light. At such speeds, they could reach Proxima Centauri in just over 20 years. Each would be small, almost fragile, but in their numbers, they could open the first true path to the stars. Like seeds scattered into the dark, hoping some will endure the journey. This shift in perspective is profound. The future of star travel may not be in building titanic vessels with thousands aboard, but in building swarms of machines smaller than your hand, emissaries of humanity racing outward faster than anything we've ever made. Still, each of these engines comes with challenges as immense as the cosmos itself. Nuclear propulsion is bound by politics and fear. Fusion is bound by technology not yet mastered. Antimatter is bound by scarcity. Solar sails are bound by the limits of materials and laser power. Breakthrough Starshot is bound by precision, by survival in deep space, and by the question of how to communicate across light years with something no bigger than a coin. Yet each is a reminder of what might be possible. Each is a sketch of a future not yet built, a hint of what humanity could achieve if we dare to think beyond the horizon. Perhaps one day, our descendants will look back at these early designs the way we look at ski, etches of Leonardo's flying machines, crude beginnings of a dream that was destined to take flight. For now, we remain on the shore, imagining the ships that might one day carry us outward. But the ocean of space is vast, and the challenges ahead are greater still. Beyond engines and propulsion lies a deeper mystery. Not just how to cross the stars, but how to endure the time such journeys demand. Because even with the most powerful engines we can imagine, the stars will never be quick to reach. And that leads us to the next question. Not of rockets or sails, but of lifetimes, civilizations, and patience measured on cosmic scales.
For as long as we've gazed at the stars, imagination has always outpaced technology. Science fiction has carried us across the galaxy on starships that bend space, through portals that link distant worlds, and into engines that outrun light itself. And in those dreams lies a tantalizing question. Are these only stories? Or could the universe truly allow them? Take the idea of the wormhole, a tunnel through space-time itself. Instead of crossing the long gulf between stars, you could step through a bridge, emerging instantly on the other side. The mathematics of Einstein's general relativity permits such structures. In theory, the fabric of space can curve so extremely that distant points fold together like paper. But the dream stumbles on the details. To hold a wormhole open, you would need what physicists call exotic matter, a form of energy with negative mass, something never observed in nature. Without it, gravity would collapse the tunnel in an instant, slamming it shut before anything could pass through. Wormholes, then, are not forbidden, but they rest on ingredients the universe may never provide. Then there is the warp drive. Popularized by science fiction, but rooted in a serious proposal by physicist Miguel Alcubierre in 1994. The idea is not to travel faster than light, but to bend the rules. Instead of moving the ship, move space itself. Compress it in front, expand it behind, and let the bubble of space-time carry you forward. Inside the bubble, you never exceed light speed, but outside, distances shrink. Once again, the math allows it, but the costs are staggering. To power a warp bubble, as Alcubierre described, you would need more energy than the mass of the universe itself. Later, refinements have reduced the requirement, but it still demands negative energy densities. Again, exotic matter beyond our reach. Warp drives sit at the edge of physics, permitted in the equations but impossible with what we know.
Other ideas orbit the same territory. The Krasnikov tube, a kind of permanent space-time tunnel carved behind a ship, allowing a one-way shortcut for future travelers. The white hole, the theoretical opposite of a black hole, spewing matter and energy outward. Even the possibility that quantum entanglement, the strange connection between particles across space, might one day be harnessed for communication faster than light. Each idea dances on the boundary between known physics and speculation, a reminder of how little we truly understand about the structure of reality. Yet for all their beauty, most of these concepts come with barriers that seem insurmountable. They require forms of energy we cannot create, stability we cannot control, and engineering far beyond imagination. Still, history teaches caution before declaring anything impossible. For centuries, heavier-than-air flight was dismissed as fantasy. Splitting the atom was once unthinkable. Even the notion of space travel itself was science fiction until it wasn't. The line between imagination and invention is often thinner than we believe. But physics also teaches humility. Some barriers are not just practical. They may be absolute. The speed of light is not merely a challenge of engineering, it is woven into the structure of the cosmos. No object with mass can accelerate past it, no signal can outrun it. To do so would unravel cause and effect, breaking the chain of time itself. So when we dream of warp drives and wormholes, we are not merely building starships, we are asking whether the laws of the universe themselves are negotiable. Whether the cosmos permits shortcuts, or whether distance and time are written into its very bones. Perhaps one day, a new physics will reveal doors we cannot yet see. Perhaps dark energy, quantum gravity, or dimensions beyond our own will provide the key. Or perhaps not. The universe may be vast, strange and mysterious, but also unyielding in its rules. And if so, then the lesson is clear. Our road to the stars will not be paved with shortcuts. It will not come from breaking the laws of physics, but from working within them. From patience, persistence, and innovation built on what the universe allows. For now, these exotic concepts remain like constellations in the sky, shining guides for our imagination, if not our technology. They remind us of possibility, even as they rest beyond our reach. But if wormholes and warp drives cannot deliver us to the stars, then another question rises. Could we ourselves endure the journey? Could a civilization outlast the distances, even if the voyage takes not decades or centuries, but thousands of years? That question, of time, of survival, and of what it means to travel without end, is where our journey now turns. When we look into the night sky, we are not only looking at stars, we are looking at possibility. Each tiny spark may be a sun like our own, and around each one, worlds may orbit, perhaps alive with oceans, forests, or cities we cannot yet imagine. But if intelligent life exists out there, how far might it go? How vast could a civilization grow? To think about this, scientists often turn to a thought experiment known as the Kardashev scale. Proposed in 1964 by the Soviet astronomer Nikolai Kardashev, it is a simple way to measure the growth of intelligence in terms of energy. For every living thing, energy is survival. For a civilization, energy is possibility. And so Kardashev asked, how much energy could the most advanced societies command? On this scale, we humans barely register. By Kardashev's definition, a Type 1 civilization is one that can use all the energy available on its home planet, not just fossil fuels or renewables, but every gust of wind, every drop of water, every ray of sunlight. We are not there yet. By most estimates, humanity is around 0.7 on this scale. A Type 2 civilization would reach far higher, harnessing the full power of its star. Imagine building vast structures around the sun to capture its light, a Dyson sphere, as the physicist Freeman Dyson envisioned in the 1960s. Not a solid shell, but perhaps a swarm of orbiting satellites, each one drinking in sunlight and beaming energy back to a home world. With such a system, a civilization could command energy on a scale beyond our comprehension, billions of times more than humanity uses today. And then there is Type 3, a civilization that harnesses the power of an entire galaxy, tapping the energy of countless stars. Such beings would be nearly godlike to us, their presence written not in cities or planets, but in galactic-scale engineering. These categories may sound like science fiction, but they are rooted in physics, not fantasy. The universe radiates energy, stars burn, galaxies shine, and in principle, any advanced society would seek to capture and use it. Energy is the foundation of survival, growth, and exploration. To imagine civilizations among the stars is to imagine what the universe itself might allow. But here lies the haunting silence. If civilizations can rise so high, where are they? If Type 2 or Type 3 societies exist, should their presence not be obvious? A Dyson sphere, for instance, would block visible light from its star, re-radiating it as heat. Astronomers have searched for such signatures, stars dimming unnaturally, glowing with excess infrared. And while there have been intriguing anomalies, no clear Dyson sphere has ever been found. Perhaps that means they do not exist, or perhaps it means they are rarer than we hope, or perhaps it means that their ambitions lie along paths we cannot yet imagine. Still, the thought is powerful. When we ask whether we can ever leave our solar system, we are not only asking about ships and journeys, we are asking what kind of civilization we might become. Could we one day build structures that encircle the sun? Could we advance from a fragile planetary species to one that commands the power of stars? The answer is uncertain, but even the act of asking stretches our perspective. It forces us to see humanity not just as we are, but as what we might become across thousands or millions of years. And there is a deeper lesson here. The Kardashev scale is not only about physics, it is also about responsibility. To reach even Type 1 requires balance with our planet, mastery of resources without self-destruction, a stable and cooperative civilization capable of enduring the long road ahead. To harness the power of a star, we must first learn to survive the power of ourselves. Perhaps this is why the stars seem silent. Civilizations may rise, but few may last long enough to climb the scale. The energy of suns may be within reach, but the wisdom to use it may be the true barrier. So as we look outward, imagining Dyson spheres glinting around distant suns, we are also looking inward, at our own fragile civilization, still learning how to wield fire without burning down the house. The night sky invites us to wonder, what forms might life take among the stars? What might civilizations far older than ours have built, and what might we one day build if we endure long enough? Because in the end, the search for civilizations among the stars is also a mirror, showing us not only what may exist out there, but what we might one day become. And as we dream of Dyson spheres and galactic empires, another thought quietly follows. If such civilizations exist, could we ever hope to meet them? Could we even recognize them? Or would they be so far beyond us that their works blend into the fabric of the universe itself? That is the mystery that now awaits us. The search for signs of life, intelligence, and technology written across the cosmos. On a summer afternoon in 1950, the physicist Enrico Fermi posed a question that has haunted us ever since. He was speaking casually with colleagues about the possibility of extraterrestrial civilizations when he suddenly asked, "Where is everybody?" It is a deceptively simple question. The universe is vast, ancient, and filled with billions of stars. Like our Sun, many of them host planets. Some of those planets may be habitable. If life is not unique to Earth, then intelligence should have emerged elsewhere. Civilizations should have risen, expanded, and perhaps reached the stars long before us. By sheer probability, the galaxy should be teeming with voices, and yet it is silent. No signals, no visitors, no Dyson spheres gleaming around distant suns, just the endless, empty dark. This is the Fermi paradox, the tension between high estimates of life's likelihood and the eerie lack of evidence for it. There are many possible answers, each unsettling in its own way. One answer is that life itself may be rare. Perhaps the leap from chemistry to biology is so improbable that it happened only once in our galaxy, here on Earth. Maybe we are the exception, not the rule. Another possibility is that simple life is common, but intelligence is rare. Microbes may thrive across countless worlds, but the fragile spark of consciousness may almost never ignite. Or, even if it does, it may not last long. That brings us to a darker possibility, that civilizations are prone to self-destruction. Technology grants power to heal, to build, but also to annihilate. Perhaps most species invent the means of their own collapse before they can reach the stars. War, climate catastrophe, resource exhaustion. The pitfalls are many, and the silence in the sky may be the silence of civilizations that failed to endure. But there is another possibility, one that suggests they may be you. They're yet invisible. Perhaps advanced civilizations are deliberately hiding. To reveal oneself in a galaxy where others may exist could be dangerous. Some call this the dark forest hypothesis, the idea that the cosmos is like a forest at night, where every civilization is a hunter, careful not to reveal its position. Any voice shouted into the dark risks drawing predators. If this is true, then the silence is not absence, it is caution, it is survival. Or perhaps the problem is not that they are silent, but that we are not listening correctly. Our search has focused mostly on radio signals, scanning the heavens for artificial broadcasts. But what if advanced civilizations have long since moved beyond radio? They might use channels we barely understand. Quantum entanglement, for example, where particles separated by vast distances remain linked in strange instantaneous ways. If that property could ever be harnessed, it could serve as a method of communication faster than light. Or perhaps they use gravitational waves, the ripples in space-time, created by massive cosmic events. These waves pass through matter effortlessly, meaning a signal sent this way would travel cleanly across the galaxy. Our detectors for such phenomena are still new, still clumsy. A civilization far older than us might use them as easily as we use satellites. And then there is the possibility that their messages are not even aimed outward. Maybe the most advanced civilizations have no need to communicate across stars because they have turned inward, into virtual worlds, into dimensions of thought and simulation that we cannot perceive. They may exist, but not in a form we could ever hope to detect. The Fermi paradox lingers because each explanation reshapes how we see ourselves. If life is rare, then we may be utterly alone, a fragile miracle in an otherwise barren galaxy. If civilizations self-destruct, then our future is a warning written in silence. If they are hiding, then the universe is darker and more dangerous than we dare imagine. And if they are speaking in ways we cannot yet understand, then the silence is not silence at all, but a failure of our own imagination. The paradox reminds us of a truth both humbling and inspiring. The search for others is also the search for ourselves. In scanning the sky, we are really asking, what is possible? What futures lie ahead of us? Are we destined to be fleeting, or could we one day join the great chorus of civilizations, if it exists? For now, the answer remains unknown. The night sky is vast, and our search has only just begun. We have listened to a whisper of the cosmos, not the whole song. And yet, there is a strange beauty in the mystery. In the silence, possibility remains open. Perhaps the galaxy is empty, and we are the first to rise, or perhaps it is full, and we simply have not learned to hear it yet. Either way, the question remains, if we cannot find them, should we continue trying? Should we send messages into the dark announcing our presence to whatever may be out there? That choice, whether to remain silent or to speak, is where our journey now turns. Life is often described as fragile, a thin film of biology clinging to a rock, orbiting a star in the vast vacuum of space. But what if this impression is wrong? What if life is not fragile at all, but resilient, persistent, restless, always searching for new shores? This idea carries a name, Panspermia. The notion that life is not confined to a single planet but may travel between worlds, carried by stones, dust, or even deliberately launched across the void. At first it sounds like science fiction, yet the deeper we look into the cosmos, the more possible it seems. Consider meteorites. Every year, fragments of Mars fall to Earth, chunks of rock ejected by ancient impacts, crossing millions of kilometers before landing on our world. We know this because these meteorites bear the unmistakable chemical fingerprint of Martian geology. If rock can make the journey, could life? Inside some meteorites, tiny pores and cracks could act as protective chambers, shielding microscopic organisms from the worst of space. Radiation, temperature extremes, and vacuum would pose threats, but not necessarily fatal ones. If microbes were trapped inside, cocooned in stone, some might survive the journey of years, even centuries, until landing on a new world. This is natural panspermia, the idea that impacts and collisions spread life from one planet to another, seeding the cosmos. Earth and Mars may not be isolated islands, but connected ecosystems exchanging the raw materials of biology. If so, then the question, did life arise on Earth, might be incomplete. Perhaps life did not originate here at all. Perhaps we are Martians, or perhaps both planets are descendants of life that began elsewhere. And then there is directed panspermia, the possibility that life is not only spread by chance, but by design. The concept was seriously considered by great scientists of the 20th century, including Francis Crick, co-discoverer of DNA's structure. They proposed that an ancient civilization, perhaps facing extinction, might deliberately launch spores of life into the galaxy, not as colonists, but as seeds. Like gardeners scattering grains of wheat, they may have aimed to ensure that life would take root, even if they themselves could not survive. It is a staggering thought. If true, then all biology on Earth may be part of a grander story, the legacy of beings we will never know, but to whom we owe our existence. Skeptics point out that we lack clear evidence for either natural or directed panspermia, but experiments here on Earth show us something remarkable. Life can survive conditions far harsher than we once believed. Consider the tardigrade, the tiny water bear that lives in moss, lichens, and soil. Barely 0.5 millimeter long, it seems unremarkable until tested. Tardigrades can survive being frozen, boiled, dried out, or blasted with radiation. They can endure pressures 6 times greater than those at the bottom of the ocean, or the near-perfect vacuum of space. In 2007, tardigrades were carried into low Earth orbit aboard a European spacecraft. Exposed directly to space for 10 days, with no air, brutal radiation, and searing sunlight. Many of them revived after returning to Earth, crawling away as if nothing had happened. Other microbes have shown similar resilience. Bacteria have survived for years on the exterior of the International Space Station, clinging to metal surfaces as they orbit Earth at thousands of kilometers per hour. Dormant spores have awakened after decades sealed away in laboratories. These discoveries hint at a startling possibility. Life may not only survive on a planet, but between planets. The void is not a perfect barrier. It may be a bridge. If panspermia is real, it changes our perspective. Life would not be a local accident, but a cosmic traveler. It would mean that biology is a process not confined to Earth, but written into the very structure of the universe, a pattern that seeks out every crack, every niche, every chance to endure. It also means that if we discover life elsewhere, on Mars, on Europa, on Enceladus, the first question we must ask is it truly alien or is it family? Does it share the same genetic code, the same molecular architecture, the same origin as life here? Finding kinship would suggest that panspermia binds the solar system into one great web of life. But finding difference, truly alien biology built on unfamiliar chemistry, would be even more profound. It would mean life does not need to spread because it arises naturally wherever conditions allow. Perhaps both are true. Perhaps the universe is seeded by both accident and inevitability, with panspermia carrying life outward and spontaneous origins igniting new sparks wherever the chemistry is right. For us, the implications reach further still. If microbes and tardigrades can make the journey between worlds, then so could we. Our spacecraft, our probes, and our future starships may one day carry not only human explorers but the essence of life itself. We may become the agents of directed panspermia, ensuring that Earth's biology continues long after our planet itself is gone. Already, some scientists propose storing capsules of genetic material, frozen embryos, seeds, or engineered microbes aboard probes bound for distant stars, not as messages to other civilizations, but as life's insurance policy. If Earth falls silent, its biology need not vanish. It may continue, scattered among the stars. There is a strange comfort in this vision. Even if humanity fails, life endures. Even if our story ends, life's journey does not. The cosmos, then, may not be empty at all. It may be alive in ways subtle and unseen. Spores drifting between worlds, seeds waiting for fertile soil, a great migration unfolding across billions of years that began long before us and will continue long after. And yet, this idea also carries a question. If life can spread so easily, then why is the universe not obviously full of it? Why do we not see oceans glistening on every world, forests rising from every planet? The answer may lie in the fragile balance between possibility and survival. Life can endure incredible extremes, but not all. Many seeds may fall on barren ground, never to sprout. Many spores may drift forever, lost in the dark. Life spreads, but only rarely takes root. Which leaves us here on a single blue planet, wondering. Are we one of countless blooms scattered across the galaxy, or are we one of the few that ever survived? The truth remains hidden in the silence of space, but the journey of life is far from over. For in the next step of our story, the question is no longer just how life spreads, but how we as conscious beings choose to carry it forward. When we imagine life beyond Earth, we often picture Earth-like planets, blue oceans, green continents, and skies washed in the light of a sun. But what if the most common homes for life in the cosmos look nothing like our own? What if life is not bound to worlds like Earth, but thrives in places far stranger, far older, and far more abundant? The search for habitats beyond Earth begins not with stars like ours, but with their quieter, dimmer cousins, the red dwarfs. Red dwarfs are the smallest stars capable of fusion, burning so slowly that they outlive suns like ours by orders of magnitude. Where our sun will last a mere 10 billion years, red dwarfs endure for trillions. They are the candles that refuse to die out, glowing faintly while the rest of the universe grows dark. In the distant future, when every star like the sun has burned away, red dwarfs will remain, tiny embers in a fading cosmos. For civilizations, that matters. Around these stars, a planet could orbit in a stable, habitable zone for longer than the current age of the universe. A world warmed by a red dwarf might not just nurture life, it might preserve it for unimaginably long spans of time. Yet these stars are not without challenges. Red dwarfs flare violently, especially in their youth, blasting their planets with radiation. Many of their habitable worlds may be tidally locked, with one side forever scorched by daylight and the other plunged into eternal night. Still, between these extremes, there may exist a twilight band, a ring of perpetual dusk where the balance is just right. Some scientists believe these narrow regions could harbor oceans, climates, and even biospheres. If so, the most enduring havens for life in the universe may not orbit suns like ours, but stars we can barely see with the naked eye. But stars are not the only possible homes. Imagine a world without a sun at all. Astronomers speak of a galactic habitable zone, a kind of cosmic Goldilocks region. Here, stars are close enough to have planets rich in metals, yet far enough from cataclysms to allow life to endure. Earth sits within such a region, perhaps not by chance, but by necessity. Civilizations may cluster here, not scattered evenly across the galaxy, but concentrated where conditions are most favorable. The idea carries a strange implication. If intelligent life exists elsewhere, perhaps it is not randomly distributed among the stars. Perhaps it gathers in great rings, arcs, or clusters across the galactic disk, habitats woven into the structure of the Milky Way itself, and this may scale beyond a single galaxy. Just as some regions within galaxies are more favorable to life, so too may some galaxies be more favorable than others. A spiral like the Milky Way, rich in metals, might be far more fertile than an elliptical galaxy stripped of gas and dust. On a cosmic scale, there may exist superhabitability, entire regions of the universe where life is more likely to thrive. When we step back, the picture shifts. Habitable worlds are not rare jewels, but potentially countless, scattered across stars, planets, and rogue wanderers. They are not limited to blue marbles like Earth, but may include dimly lit seas under ice, perpetual dusks around red dwarfs, and civilizations cloaked in darkness. And yet there is a paradox here. If the galaxy is filled with possible homes, why do we not already see them? If life has so many opportunities, why does the night remain silent? Perhaps the answer lies not only in where life can exist, but in where it can endure, and in the challenges that await any civilization that dares to rise among the stars. For as vast as the universe's habitats may be, their silence still calls to us, leading us to a question that is as haunting as it is profound. The story of the universe is a story of time, not centuries, not millennia, but spans so vast they defy human imagination. Stars are born and die in silence, galaxies collide and merge, and whole epochs pass unnoticed in the abyss. Against this backdrop, humanity's existence is a flicker, a fragile flame trembling in cosmic winds. And yet, we dare to ask, what comes next? Not just for us, but for everything. What does the universe look like in its long future? And could intelligence, perhaps even ours, survive the slow unraveling of eternity? The tale begins with our sun. In 5 billion years, it will swell into a red giant, swallowing Mercury and Venus, scorching Earth beyond recognition. Its outer layers will drift away, leaving behind a white dwarf, a stellar ember, glowing faintly in the dark. For us, this might seem like the end. But in cosmic terms, it is only a beginning. White dwarfs will cool. Stars like ours will fade. But the red dwarfs, those ancient steady fires, will endure for trillions of years, outliving the universe as we know it today. For future civilizations, if they exist, such stars may become their final sanctuaries, tiny red suns glowing faintly in an increasingly empty cosmos. But even they cannot last forever. In time, all stars will burn out. The galaxy will go dark. Planets, asteroids, and dead stars will wander, colliding or drifting endlessly. Black holes will dominate, swallowing what remains. For hundreds of trillions of years, the universe will be ruled by shadows. This is the age of entropy, the slow, inevitable march toward disorder. It is a principle of physics as fundamental as gravity. Over time, energy spreads, systems decay, and the cosmos moves toward equilibrium. And equilibrium, in the farthest future, means heat death. A state where all usable energy is spent, where no stars shine, no engines burn, no life sits. In this way, a mind might experience eternity even as the universe fades. Not as continuous thought, but as scattered sparks across the darkness, stretching survival to its absolute limit. And yet, even these strategies meet a wall. Entropy grows. Energy dwindles. In the end, the cosmos trends toward silence. Does this mean intelligence is doomed? Perhaps, but perhaps survival is not only about resisting the universe's fate, but adapting to it. Could minds evolve beyond matter, beyond energy, into forms we cannot imagine, patterns of information embedded in the very fabric of space-time? Could intelligence outlast stars by becoming something entirely new? These are speculations, hovering at the edge of science and philosophy. But they reveal a deeper truth. Survival in the long future is not merely about physics. It is about choice, and here, humanity stands at a crossroads. We are the first species on Earth to glimpse the universe's destiny. We know our sun will die. We know the cosmos itself is finite. And we know that life, fragile as it is, will vanish if it remains bound to a single world. Our choice is stark. Remain here, tethered to Earth, and accept extinction as our fate, or take the harder path, to become a spacefaring civilization, spreading into the stars, carrying life beyond the cradle that bore it. For now, this may seem like fantasy, but every great journey begins with a first step. The Voyager probes drift outward. Telescopes map distant worlds. Ideas of fusion drives, solar sails, and Starshot missions take shape. Each is a whisper of a possible future, a seed of a civilization that might one day claim the stars as its own. If we succeed, then perhaps our descendants, in whatever form they take, will witness epochs we can scarcely imagine. They may see the last stars fade. They may live beneath red dwarfs for trillions of years. They may